All right, hi there. Welcome back. Here's the next lesson. All right. So first, let's talk about flooding. What are the reasons that we might have flooding? Okay. What are the reasons? So, I mean, some of these you probably would expect, right? The number one, heavy rain. If we get a lot of rain, um, in a short period of time, combined with some of these other factors, we could definitely get flooding. Um, Also, if there's rapid snow melt, like let's say we have a high pressure system freaking sitting over a mountain, oh, that could cause rapid snow melt. Um, and then you have to think about your drainage area. Like, is there a place for the water to run into? Like, is there a river nearby? What is the, flood basin like? Floodplain. Um, Topography you have to think about because, the valleys are going to flood. Um, A good thing to think about, a good example is um, Hurricane Helene. Obviously, there was flooding. That was like the pretty much worst impacts from it, right? And I'm just saying that because that happened this year. You might be watching this in a different year, so whatever. There's probably gonna be another hurricane that's like that, you know. But this is just an example. Hurricane Helene that was in 2024. In Asheville, some of the elevations where it flooded the worst are lowest, because obviously everything's going to go down. So that matters too. What the sorry, topography is. Can't speak, apparently. Whatever. Uh, Impervious surfaces. What does that mean? And I'm sorry to just have text on here. Like maybe I should have some pictures, but um, when we're talking about impervious surfaces, we're talking about the fact that when we have just grass or dirt, whatever, the water can, soak into that, right? But if we have like sidewalks, asphalt, it's going to be hard for that water to soak into that. It can't really, depending on what kind it is, especially the new, like black asphalt that's new. That's even harder for it to soak into. So it's going to flood worse in places like that. Good example, combination of some of these things. Um, Charleston, South Carolina. Um, Specifically, a part that floods a lot is like, and it's not just because of this, but the part, um, like the main like street area. I don't know if it's Rainbow Row or whatever, but there's like um, just off the coast. Um, you have to think like when there is heavy rain there, it's harder for it to soak in. And obviously, there's other reasons why that floods, and we're going to talk about that later. Um, because for that, that's not just the factor. But then you have to think of soil types. Some types of soil are better at soaking it in than others. Let's talk about river floods. I don't know why that picture's so glitchy. Sorry about that. River floods are actually not that common, because, rivers are really big. It's going to take a lot for a river to flood. So it's only usually possible if there's a large weather system, like tropical cyclones. So if a hurricane comes through, yes, it's certainly possible a river could flood. But from just a afternoon tea storm, probably not. So river floods are actually not too concerning to us because they're easy to predict because, like I said, the only thing that can really cause them is something that we know far in advance. So that's not saying it's not a problem, it's just saying it's easy to predict. Coastal floods, that might be caused by storm surge or onshore winds. So this is what I was talking about. This picture is Charleston, South Carolina. And look at that right there. I mean, the water's not going to soak into that, right? It's not going to into that road right there. And that's not the only reason. Like we have storm surge. And if you don't remember what that is, um, essentially like let's just say, for example, storm surge from a hurricane. We have like strong winds in the ocean, and it's a surge. It's not actually rainfall. Like that's a common misconception. The storm surge is not rainfall. So if you hear 7 feet of storm surge, that's not going to be, hopefully, that's not going to mean 7 feet of rainfall. That's meaning that that's how much it's expected to rise from the surge that's out in the ocean that's getting pushed towards shore. Then, of course, we have onshore winds. We talked about that before about how there's, depending on the time of day, we sometimes have, we have sea, land breezes, but that can actually have an impact. Too. But this is once again easy to predict, so it's not really much of a problem. But what we really care about the most are flash floods. Flash floods are caused by excessive rain in a short period of time, and it can happen pretty unexpectedly too, because sometimes we may know there's a risk for severe weather, but we don't really know exactly where that's going to be. We don't have technology, so that's why this is the biggest deal because we can say, okay, well, we're gonna, issue a severe weather watch for this large area of the state, but it could end up only being one town that gets flooded, like gets a flash flood, and that's the issue. Like a lot of people, they've done studies on this. When people see like a tornado warning, or a severe thunderstorm warning or something like that, like they take more action than if they see a flash flood warning because there's like, like, whatever. But flash flood warnings, sometimes you might be under a flash flood warning and nothing will happen to you. But that's because they issue it for a pretty large area because they don't know specifically where it's going to be. But um, there Ellicott City is an example of a place in Maryland that received two very rare um, and extreme floods. I believe the years were 2016, 2018, the two major floods there. And um, you could see the video. It in such a short amount of time, I think within like um, hour and a half, like a few inches of rain fell down and it just immediately caused devastation. So this is what we're talking about. It's like it went from just a normal day to hour and a half later, okay, that's not so good. If we're talking about return periods, if you hear something like, oh, that was 100-year flood, a lot of people think that means it's only going to happen one time in 100 years. But that's not what that means. It means actually you have to consider it as a percentage. It means that there's a 1% chance that it could happen in any year. So if it could happen, if it's saying 100-year flood, it's saying there's a 1 in 100 chance of it happening every year. It doesn't mean if a 100-year flood happened in 2022, oh, there's not going to be another one until 2122. No, there could definitely be another one. Um, but an issue with these, you know, terms when you'll hear people say, "Oh, that was a 100-year flood, that was a whatever," is these are actually outdated because a lot of them were labeled or whatever you would say, like in the 60s. And as we know, the climate has changed a lot since then, in 60 years. And, we have a lot of changes, so we might need to update those. So, yeah. All right, moving on. Um, so I'm not going to go too much into detail about this, but there are different types of snowflakes. And what creates the different types are different temperatures. And the thing about snowflakes, you may have heard this before, it's actually true that no snowflake is exactly the same as another. There's some that can be similar, which are labeled in these, but that obviously you may have known if you live in a place where it snows that um, sometimes the snow can be different than other times. Like maybe sometimes it's wet and kind of nasty, or sometimes it's more white and like fluffy, and that all depends on temperature. Let's look at right here we have normal annual snowfall 1981 to 2010. So sorry, that's kind of outdated, but whatever. Um, let's see what we have here. So just, look at this thing, okay? All right. Well, we're not seeing anything down here, right? Not really. It's rare to get snow here. So I did one time live around here in South Carolina. And no, like in the about 5, 6 years that I lived there, I saw snow only one time on January 29th, 2022. And of course it didn't accumulate. But you just go a little bit more north and then you will see some snow. And we see some places that where's there the highest? So we see, okay, right over here in Colorado, we might expect, Rocky Mountains. And then we see here, this is Buffalo, New York, around here, and we're going to talk about in a second why there's so much snow there. Look at that. That's over 120 inches. That's a lot. And then we have a little outlier right here. Oh, shoot. I don't know if you heard that. My computer's about to die, so gotta pause this for a second. Okay, that's better. My computer doesn't really have very good charge. It's kind of annoying, honestly. Um, okay, so I was saying we have an outlier here in northwest, or sorry, northeast West Virginia. Um, there's an interesting that's an interesting area right there. It actually has some of the coldest temperatures in the whole country. But not going to talk about that right now. Now, we don't have to only think about the United States. We can look, okay, we know nothing in Mexico, right? Okay. All right, go up, Canada, right? We see a lot, and then we don't see that much right here. What's the deal with that? How come and Greenland is omitted right here, but what's the deal? Why do we not? I know there might be snow right there, but there's not as much. Well, that's actually because there's lower moisture. If you remember, different places where we have high or low pressure centers, that's actually a place where we have high pressure at the pole. And as a result, there's lower moisture, so it's not as easy for there to be snowfall. So, in case you didn't know, not much snowfall up there in the North Pole for Mr. Claus. Okay. Oh, what the heck was that? Oh, forgot I put that picture in there. Ooh, that kind of freaked me out for a second, honestly. Ooh, I made the slideshow a few days ago. I didn't remember what I did. Okay. Lake effect snow. Have you ever heard of this? Well, this explains why we have so much snow right here in Buffalo, New York. Lake effect snow. What happens essentially is we have a lake that is warm because we know water cannot cool down as fast. So it's going to be warmer than the land, right? We have cold air coming from the west, right? It's just as a fun fact, or not really fun fact, but whatever. Um, in the United States, almost everything comes from the West. If you ever look at the radar, if you notice, almost always the thunderstorms come from the West. That's just almost always what it is. Right now, we're not going to talk about why. That's actually what's going to be in future lectures. But that's what you need to know. So that if you see the freaking what do you call it? Legend is not in this picture for some reason, but this yellow right here is supposed to mean there's way less snow on the west side of this lake. And the reason why is that we don't have, it's not going that way. It's not easterly, it's westerly. Remember, winds are named from where they come. So if I say westerly, it's coming from the west. And look at that large distance that it goes. It cruises right over that thing. There we go. And snow, a lot of snow right there. We have cold air passing over a warm lake, and that difference in temperature is what um, results in high precipitation. And then, guess what? Snow. Shing, shing, shing. And the lakes have to be really big for this to work. So if we're obviously we know the Great Lakes are the biggest lakes that we have. Um, but if we're talking about a smaller lake, like I don't really want to give an example, in case you don't know what I'm talking about, but um, there's a lake called Lake Marion in South Carolina, for example. Like that's just the one that I could think off the top of my head. It's a big lake, but it's not big enough for this lake snow effect. And anyways, that we don't really get snow down there. But if we did, that's not big enough. Okay. All right, now let's talk about LCL. If anyone says LCL, that refers to lifting condensation level. And what does that simply mean? It just isn't it's an altitude, and it's the altitude for saturation. So remember, where we have saturation, we are going to have the temperature that's equaling the dew point. We're going to have relative humidity 100%. We're going to have, that's going to be where the cloud base begins. So where the LCL is basically the bottom of the clouds, okay? Um, if we have fog, then the LCL equals 0 meters because fog basically is a cloud that's on the ground. But in general, the way that we can calculate this don't really have to memorize this, but 125 times um, temperature times minus the dew point temperature in degrees Celsius. So if you do that calculation, T minus dew point T, and you multiply that by 125, you can freaking say, with a rough estimate, as you can see, approximate, where the cloud base is above you. Um, what are the ways that air can be lifted? Okay. We have four main ways. The first is convection. Convection is like the pretty most straightforward that you probably have already know. You hear warm air rises, cold air sinks. That is what convection is. I mean, it's simple as that. You can see over here we have solar heating, and then that hot air reflects back. Um, and that long wave radiation, it rises and cool air will sink as well. The next is orographic lifting. That's talking that you see what I put there, mountain up, so that the air is like crashes into that mountain. It's like can't go through the mountain, it goes up. It's like, there you go. So that kind of makes sense, right? Like most of these just actually make sense. Like the air's not going to just stop or something. It goes. And this is important because we're actually going to find out that on the other side of this mountain right here, it's going to be pretty dry. And that's because of this. Other things too, but this leeward side is what it's called. It's going to be dry. Frontal lifting. The frontal lifting is right here, and happens kind of when we have a collision of warm and cool air. And we could say when we have a cold front. And what's always going to happen is that the warm air is going to go on top of the cold air. So warm on top of cold. And then the last is convergence. If we literally have two air masses that run into each other, they're going to go and just converge and go up and rise. So those are the four different mechanisms. All right, now let's talk about some lapse rates. And these are going to be lapse rates for air parcels. We're going to talk about the environmental lapse rate too, but right now we're talking about just for air parcels. So like a little small thing, not the whole environment, okay? How you calculate this is the change in temperature over the change in height. And we have two different lapse rates. And the first one is DALR. This is the dry, uh, which means unsaturated adiabatic lapse rate. This one is the same always, which is about 10. Um, and then the saturated adiabatic lapse rate it can vary from 3 to 8. And if we're having 3, that's going to be more moist. And then 8 is going to be more dry. And that makes sense, right? Because it's closer to 10. And if we get to 10, then that's the dry, right? Um, we can And what we end up doing is changing from the dry one to the saturated one as we rise. 99.9% of the time, we will start with the dry one, okay? So it's very rare that it's going to be saturated to start. Um, and then that's when we're going up. When we're going down, it's always going to be, we'll look in a second, okay? Not to spoil it. Now, the ELR is the environmental lapse rate. So we're talking about like the surrounding area. This is not something that you can calculate off the top of your head like the others, or like just have a number ready to go. This is why we use weather balloons. We're able to know by them. So let's look at this example. Don't get freaked out by this. It's not too bad, okay? It's not. So remember I told you the environmental lapse rate, change in temperature over change in height. Um, but we're going to say that 1 kilometer right here is the LCL. Now, how am I saying that? Because these two numbers are the same. That's exactly how. And I know these are too, but we're talking about the first point where they're the same. So right here, we're like, okay, saturated. When the two numbers are the same, um, because see this is saying this is the temperature of the parcel, this is the dew point temperature of the parcel. Whenever they're the same, we have relative humidity of 100%, and that also means we're saturated, and that also means that's where the cloud base starts. So what we're going to use to be able to know, this is how we're able to know what the new temperature is going to be. So we're starting out with 26, and it's in Celsius, by the way. We're going to say, okay, we're rising. We know as altitude increases, temperature decreases. So we're going to subtract. Now, do we use the dry or saturated? I told you all, pretty much we can say all the time you start with the dry, and that's 10. And we definitely know that we're going to do it because they're different. They're different numbers right here. See, 26, 16. That means we have to use the 10. So we do minus 10, and then ding, ding, ding. Now they're the same. So now we switch over to the saturated lapse rate, which in this case, it would be 5. And that one can vary, so you'll just be told on the question. So it could be 3 to 8. And as you can see here, it's 5. It's minus 5, minus 5. Now, if you get questions about this, um, the first thing you're gonna think about is it saturated or unsaturated? And how we know is if these numbers are the same. So not the same, unsaturated, same, saturated, same, saturated, same, saturated. And that tells us which lapse rate to use. We use dry, we use saturated, we use saturated, we use saturated. And we know it's going to get lower in temperature as we go up. So we will just, that's the way we do it. And this is going up a mountain in this example. Now, when we're going down, as I hinted at before, we only use dry when we're going down. So always 10 because basically it's not possible for sinking air to be saturated. That's, I'm not going to get into specifics of why right now, but that's just what you need to know. We're always using the dry adiabatic lapse rate when we're going down. So 6, 16, 26, 36, ding, ding, ding. Yeah. All right, let's talk about stability now. If an air parcel is warmer than its surroundings, it will rise. And when that happens, it is considered unstable because the temperature of the parcel is higher than the air. Now, if it's colder, it will sink, and that's stable. So once again, I'll say, if the temperature of the parcel is higher than the surroundings, it's rising. And when it's rising, that is unstable. Unstable meaning that's going to result in weather that is everything in the atmosphere strives for balance. You could really argue in every aspect of the world, um, but that just we don't need to get too like philosophical right here, okay? We don't. But balance is like the key to everything, it seems like in the universe. And so whenever something's unstable, there has to be something that occurs to fix that for almost everything, okay? Um, everything ends up evening out. So if we have unstable parcel that's rising, because it's hotter than its surroundings, then that means there's going to be something that needs to bring it back to stability. Sometimes that can be a thunderstorm, sometimes that can be a tornado. So that's like on a basic level why we have those things. And however, if it's sinking, it's stable, and that means that we're in that case, we might expect more like calm conditions. And then the third one I didn't even mention because it's not really common at all. That's if it's the exact same. That's just not really in real life, that's not really that common for it to just be exactly the same. Now let's look at some graphs here. So with these graphs, we have three different lines, and you don't even have to know, um, you don't really have to know exactly like how what I don't know how to put this. You don't have to like understand every aspect about the graph, but just look at notice the order of these three lines. And when you're seeing that order, that should tell you what is going on. So we see here we have the blue, green, and red. Environmental lapse rate, dry, saturated. Um, the blue and the green are always going to stay put. So we're always going to have the blue one before the green. So don't even we don't even care about those because I'm going to have like five of these and they're always going to be in the same place. We care about where this red one is. We see that this red one is on the left side of both of those. This is unstable. So the environmental lapse rate is to the left of them. And that kind of makes sense of what we just said because that means their temperatures are higher and they're that I told you before if this the parcel is higher than unstable. Now we this is the reverse. Now that red thing went and it's on the other side, so that means that sorry. That means that this time the parcel, which is the green and blue, is colder than the environment, so uh stable. Dry and sunny is what we would expect over here. Possible thunderstorm. I'm sorry, there's something right there I can't see. Oh yeah. Saturated is always to the right of dry. All right. Third one is whoa. Duh, 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 duh. What the heck happened to that thing? Why did it go crazy and now it's like pointed the other way? And you might think, ooh, that must be like some kind of crazy thing. And it kind of is. This means it's still stable because it's still the green and blue are colder than the red, but it means an inversion. So if it's going to go crazy like that, and instead of over here, like look what's happening. We're seeing that as height increases, temperature decreases, but for here it's the reverse. As height increases, temperature increases. So that means an inversion because we know that after we get past tropopause into the stratosphere, we have an inversion, and at that inversion we have temperature that is rising with altitude instead of sinking. That just goes back to our earlier videos. So that's like, ooh, what the heck? If you see that one, that's not really going to be a thing. But I just put it there so you would know, okay? Now, ooh, last one, right? Yeah, last one. It's in between. So what does that mean? It means conditional. It means it could be stable, it could be unstable. And it's almost like you can just memorize these, but you can also just logically think about it. I say that if the parcel is hotter or warmer than the red, then unstable, opposite stable. So the green one is warmer than the red one. So that means we're basically saying saturated, unstable, but the blue one is colder. So if it is unsaturated, stable. So that's why it's conditional. Conditional meaning that it could be either one, but it depends on which you're talking about. So if it's saturated, it's going to be unstable. Unsaturated is stable. You could just memorize that, or you could just look at it and see, oh, this one's to the right. To the right, if the green or blue are to the right of the red, then it's unstable. Opposite, stable. Now, how do we get instability? And why do we care about this? Okay. We care about this because the severe weather, I already said, it's why things happen is to achieve stability once again. Um, Everything's shifting around, and we need to heat up a surface and we need to cool down the upper troposphere. And why? Because we any difference is instability. And we're going to look right here. This is a definitely a thunderstorm, and we're going to talk about that. But we see some characteristics here. We have this flat part here that's called an anvil. And why is it like that? Because we have the tropopause, so it's like, remember I said before, like it's a good thing we have this inversion because otherwise this thing could keep going higher. It could be like dun, 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 and just keep going like as far as it could go. And then we would have insane thunderstorms. Like we might have like hailstones the size of houses, like just smashing down on the ground. That would be horrible. Like, no human survival for that. So good that we have that inversion. That's why the thunderstorm's like, ha 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 ha, like it gets to rise and it's like, oh, come on. It stops. That's what that anvil is. But we get something kind of crazy in here. It was like, ooh, too bad. And a little part of it went into the stratosphere. So it's like, ooh, that's called an overshooting top. You see that little these two white things that are higher than the anvil. That's like it's saying too bad. I'm gonna sneak up here anyways. And because it did that, that's a possible indication of tornadoes. That's one way that we can uh, look at that. So, ooh. Um, Now we're gonna talk about something called entrainment. Entrainment means if we have dry air sneaking into a thunderstorm. Dry air is like, oh, like, the party pooper of this thunderstorm. It just makes it die, basically. So there's a way to visually tell this, which I'm not going to say in this video, but this is what some people that are chasing storms will look at. They'll be like, I can see that dry air going in there. This isn't going to be anything for me to watch. So that's what entrainment is. All right. Coming down on the last couple topics, we're definitely going to talk more about this in the next video, pressure gradient force. PGF. The pressure gradient force is basically just a force that relating to our winds. And we're going to say the speed of wind is proportional to the pressure gradient. And the thing about pressure gradients is we air is always going to move from high pressure to low pressure. Now let's think about why. I already said so many times that the universe, I don't even really need to get that broad, but we can say the atmosphere strives for stability. So it only makes sense that if there's a difference in pressure, that the air would do something. Now, would it make sense for it to go low to high? No, it wouldn't, because if there's trying to be balanced and it's trying to be the same for both. If we're taking something away from the low, that's making it even bigger of a difference. So that's a way that's easy to remember, that it goes from high to low. So right here, if we're going to know that the winds are going to go like that, but not necessarily just like that because we have other things we'll talk about later on. But for now, this is what we need to know. This is what the pressure gradient force is. And the more gradient there is, stronger winds. So we see 1020, 980. If it was even bigger difference, then that's why we have stronger winds. And ooh, that's exactly why that there's such strong winds in hurricanes because we have the center of the low, and then out just outside the hurricane, it's a big difference in pressure, and it's going. And then tornado is almost like an even more like minimized version that's crazy because there's such a low pressure. So that's what we're talking about when we're talking about pressure gradient force. We can say the change in pressure divided by the change in distance for that. The last minor thing that I'll talk about is you need to just know something about heat waves. I was supposed to talk about this before, I forgot to, but Um, what heat waves is definitely one of the it used to be, I think, the highest weather related death, but I believe it's now flash flooding instead. Turn around, don't drown. Some people don't really listen to that, but heat waves, a lot of people will die from heat waves, not just because, oh, whatever, like they just were out in the heat or something. Like there's important things that your body does when you sleep at night, and one of those things is that it cools down. Well, it's not going to, especially in places where there's no air conditioning. It's not going to during a heat wave. In the 1995 Chicago wave, that's like the important one you want to remember. We had 739 heat-related deaths. That's really not good. Um, and 1995, obviously, compared to now, way less people had air conditioning, so that contributed to it. But you look at specifically at the like demographics, people like lower income, it, and elderly were the ones that died the most because either they, and that's both are almost the same reason because a lot of older people didn't have air conditioners, and then lower income people might not be able to afford them. But like the elderly people, oh, I didn't need those in my days. That's what some people might have been saying in 1995, and then well, in the 60s we didn't need that, but unfortunately, like this was a major heat wave, and a lot of these people that died were elderly. And you have to consider they might have that's going to affect that too because they have underlying health issues already. But that's all for this video and this section of meteorology intro. We're just talking about the basics, obviously, but we're going to get more into the winds soon and then eventually into severe weather. So, thank you.